All right. Chapter 5. Okay, membrane dynamics. Again, this chapter is pretty intense. So I'll try to go over it slowly. Okay, there might be a lot of concepts that you don't really understand. Okay, especially 5.1 and 5.7 and 5.8. Okay, homeostasis is where your body is designed to be. Okay, and your body works hard to keep it in homeostasis. Equilibrium is what will happen to you if you were dead. Okay, because that's the direction the fluids and atoms in your body will regulate themselves. Okay. Okay. So the fluid compartments. Okay. So cells have interstitial fluid. This is the vast majority of the fluid inside your body. And then the extracellular fluid is divided into two compartments. One is interstitial, which is the fluid around the cells. And then the plasma is the fluid that's actually in the bloodstream. There's not that much difference between interstitial fluid and blood plasma, other than the blood proteins that stay inside of blood. Okay, so there's always going to be leakage in these blood vessels, especially in the capillaries. Okay, and they will exchange fluids. Okay, with the exception of the plasma proteins that stay inside the plasma, and obviously the red blood cells that stay inside the blood vessels. Okay, so that there. Okay, that's another way of expressing what everything I just said. Okay, okay. So here is the key difference. Okay, so intercellular fluid and interstitial fluid are very different. Okay, notice the sodium is much higher in the interstitial fluid. It's not in the intercellular fluid, very little, and the sodium is the exact opposite. Okay, and you'll see the interstitial fluid and the plasma are more or less identical. There's slight concentrations off from each other, but not anything relevant. But the proteins are only in the plasma. Okay. 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 So you can look at that. Okay. So our water content actually declines as we get older. Okay, and this is actually something that will lead to issues like later in life, like herniated discs and uh, sciatica and stuff is due to changes in water amount. Okay, your body is in osmotic equilibrium. Okay, so osmosis. Okay, I'm sure you guys kind of heard of osmosis before, but I will explain to you guys on a slightly different level. Okay. Um, okay. So if you look at this selectively permeable membrane, okay, and you have glucose molecules. Hopefully by this time you guys will have done this lab, so it actually makes a little bit more sense. But it was selectively permeable membrane that allows things to cross, but not glucose. Okay, there is more glucose on this side and less glucose on this side. Okay, so but the glucose cannot cross. Okay, so when you have a semi-permeable membrane, okay, one of two things happen. Okay, if the molecule that you're looking at is permeable, then it will go across the semi-permeable membrane and water will remain the same on both sides. If the if the solute is not permeable, then the solution will cross. So the water will cross to try to make things equal on both sides. Okay, so here the water will cross to try to make it equal on both sides. So by water crossing from A to B here, you're pushing. Okay, the water pushes across, and therefore you generate a volume increase. Okay, so that generates a pressure. That pressure can be calculated by pushing back. So if I push this back, I know how much I have to push to maintain this gradient here. Okay, so I can talk about osmosis in terms of water moving. I can also talk about osmosis in terms of pressure, osmotic pressure. That's the pressure that is necessary to maintain the gradient. Okay. All right. So in chemistry, and when you're making solutions, you deal with molar solutions. Molar is versus the concentration of one thing. Osmolarity expresses the number of active particles, the total number of floating things that are in the solution. And osmolarity is much more relevant for physiology. So we don't really talk about molar solutions in like something like plasma. There's so many different things that dissolve in plasma. It is hard to calculate the molar concentration of one thing, but we can calculate the total number of particles. Okay, and different things will dissolve differently. Okay, I'll get to the example later. For all intents and purposes, for you guys, osmolarity and osmolality is the same thing. Just in physio, the blood has a lot of things dissolved in it, but there's the concentrations of those things are very, very little. So overall, it's very, very little. And with overall very little, the osmolarity and osmolality mean basically the same thing. Okay. ISO is the same. Hyper is more. Hypo is less. Okay, so isoosmotic, the two solutions are the same. So hyperosmotic, if A is hyperosmotic to B, then A has more particles than B does. Okay, if A is hypoosmotic to B, then A has less particles in solution than B does. Okay. Okay. Same thing for tonic. Tonic actually describes what will happen to the cell. So tonicity only applies to cells. Okay. Osmolarity applies to solutions. Tonicity applies to cells. Okay. Isotonic means the two cells, the isotonic means the cell and its environment have no pressure, so there's no water flow. So there's no movement of water. Hypertonic means the solution outside is much more concentrated, so water will flow out. Hypotonic means the water outside is less concentrated, so the water will flow in. Okay, so the difference, and I'm sure they stated somewhere else, okay, is penetrating versus non-penetrating solids. Okay, osmolarity deals with all solids. Okay, tonicity only depends on the concentration of non-penetrating solids, because non-penetrating solids will not be able to move across the semi-permeable membrane, and therefore water will have to leave or enter the membrane, and that is what affects tonicity. Okay. All right. So the osmolarity of a solution is not an accurate predictor of this tonicity because, okay, because you have to separate into non-penetrating and penetrative solvents. Okay. So if something is hypotonic, okay, it can be hypoosmotic, it can be isoosmotic, it can be hyperosmotic. Okay. Okay. So make sure you kind of understand this chart. Like if something's isotonic, it can't be hyperosmotic because that would mean there's nothing in the solution. But you can be isoosmotic or you can be hyperosmotic. So again, if you understand this chart here, then figure 5.3, then you kind of understand what the differences between tonicity and osmolarity are. Okay. Okay. So just a quick example of what is penetrable and non-penetrable. Okay. Small non-polar molecules are going to be penetrable because when we talk about this in physiology, we're usually talking about the cell membrane being the semi-permeable membrane. So anything that can cross the cell membrane, okay, is going to be a penetrating solvent. Anything that cannot cross the membrane, okay, will be a non-penetrating solvent. So salts, sugars are non-penetrating solvents. Okay, urea, CO2, oxygen, these are penetrating solvents. Okay. All right, so for all problems, define your starting conditions. So assume all initial solutes are non-penetrating and remain either in the ECF or ICF. So just think of this way, non-penetrating, it can't, if it's non-penetrating solute, then it can't cross this line. Okay. However, the body compartments are in osmotic equilibrium, so something has to cross the line. So water, okay, or the non-penetrating solute. Okay, all right. So we have a 3-liter body. This is a very small person. So we have a 3-liter body that is 300 osmolar or milliosmolar. The ECF is 1 liter and the ICF is 2 liters. So we set this up right here. So this is 1 liter, this is 2 liters. Okay. Okay. So it tells you the body is 300 milliosmolar. So 300 milliosmolar times 2 liters will mean that there's 600 milliosmol. Okay. Sorry. Okay. Yeah. So 300 times 2 liters. Okay. 300 milliosmol per liter. Okay. Times 2 liters means 600 milliosmol. Okay. Of non-penetrating solutes in the ICF. Okay. I wish the first time they did this, they wrote out the terms and stop using abbreviations, but I'm gonna try to do that. Okay. So okay, in the ECF, okay, the solution, there's only 1 liter of it. There's 300 milliosmol osmol per liter, so you have 300 milliosmol of non-penetrating solids in ECF. Okay, so it looks like this. Okay, so whenever you try to solve these problems, make sure you add the chart. Okay, okay, so 900, okay, 300, 600. Okay, so these two, okay, first of all, these two numbers have to add up to this one. Okay, so if I know this, I know this, I can solve for that. Okay, so this plus this always has to equal that. Okay, so for these two rows, okay, the total body has to equal ECF plus, oh, sorry, the, that's not ECF. This should be ICF. Okay, the ICF and ECF should equal the total body. Okay. For osmolarity, osmolarity is a concentration, not a volume. Okay, not a total amount. The concentration should be the same all throughout. Okay, you cannot add or subtract concentration. It doesn't work. You can calculate concentrations by taking the solute divided by the volume, and then you can find the new osmolarity. Okay. All right, so let's take a look at what the problem is. So example 1, okay, I add an IV solution of 300 milliosmolar NaCl to this body. Okay, so first thing, when I add fluid to the body, I'm adding the fluid to the ICF, not, oh, sorry, I'm adding the fluid to the ECF, not the ICF, right? I'm putting it into the plasma, which means it goes into the extracellular fluid, but not intercellular. Okay, so I add 1 liter of 300 milliosmolar, so 1 liter, 1 liter times 300 milliosmol per liter. So that cancels out. So I have 300 milliosmol. Okay, the 300 added to 900 means there's 1200 now. Okay, and I have 4 liters of volume now. Okay, and therefore my osmolarity is 1200 divided by 4, which is still 300. Okay, 300 milliosmol sodium sodium chloride is actually also known as saline. Okay, that's what saline solution actually is. Okay. All right, so now I know this information. Okay, the salt cannot cross from the ECF to the ICF. Okay, so the salt all goes in. Okay, so now I have 2 liters in here. I have 2 liters there because I can only add the fluid to the ECF initially. Okay, so I can calculate the new volume, and the new volume is exactly 2 liters and 2 liters. Okay. Okay, the added solution was isoosmotic, and it's all penetrating solutes, it's all the same. Okay, so there's no water leaving or entering the cells. Okay, so that is what happens when you inject your body with saline. And the answer is nothing really happens. You just get more volume. Okay, which is the whole purpose of saline. Okay. Now let's take a look. Okay, so let's take a look at example number 2 now. Okay, this is much harder. Okay, so add 2 liters of a 500 milliosmolar solution. Okay, the solution has equal parts sodium chloride, so salt that is non-penetrating, and the urea that is penetrating. So it has 250 milliosmolar NaCl and 250 milliosmolar urea. Okay. Okay, I'm adding 2 liters of this. Okay, so okay. 2 liters multiplied by 500, 250, so 250 millimole per liter. Okay, so two liters times 250 milliosmol per liter will equal 500 milliosmol of NaCl. L there, and 500 milliosmol of urea. Okay, just remember urea is penetrating and salt is non-penetrating. Okay, so salt will cause water to move around, urea will not. Okay. 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 So what do you add? Blah, blah. So I added, 500 millimolar milliosmolar urea, 500 milliosmolar NaCl. Okay. So the first thing I look at is the water and the NaCl first. Okay. Okay. So simple. Okay. I add the non-penetrating solutes. Okay. So 900, which is originally the body, plus 500 instead of 1400. Okay. I had 3 liters of fluid. I add 2 liters of fluid. Okay, and now I end up with 5 liters. Okay, so that's my osmolarity. Okay, 280 milliosmolar. Okay, now those are the salts that will change the volume of the ECF and ICF. Okay, so I have, since the solvent can't move, okay, this was originally 300. I added 500 to it since the salt, I added 500 osmolar here. Okay, so that 300 plus 500 is 800. So now I have more salt on the outside and less salt on the inside of the cell. Okay, so now that also means I must have more fluid on the outside of the cell and then inside of the cell. Okay, I know the osmolarity because the osmolarity has to be equal on the inside and the outside. So 800 divided by 280 is 2.85. So I have that much volume, and then 600 divided by 2.80 is 2.1. Okay, so I have 2.8 liters on the outside and 2.1 liters on the inside. Okay, so to get this, just to make sure I see it, to get this, I get 800 divided by that. Just use that. Okay, 600 divided by 280 equals that. Okay, so that's how I solve for the new volume. Okay. Okay. So basically, the first part I'm solving for the whole body here. I come up with this value. This value automatically goes into 1, 2, 3 columns. These all have to be the same. Okay. Okay. So now I know what the volume of the ECF, ICF. I know what the I know the volume. Okay. But now comes the next part. The next part, I have to add the concentration of the penetrating solvents. We completely ignore that initially. Okay. The penetrating solvents, since it will penetrate, it will just spread out evenly throughout. Okay. So I'm adding another 500 milliosmoles there. Okay, so I get 1900 total. So I start off with 1400. Now I'm adding another 500, and now I'm just the volume stays the same because the urea can cross the membrane, so it doesn't change extracellular fluid volume or intercellular fluid volume, and so it just changes the osmoles. So 1900 divided by 5 is 3. 380. So there we go. Okay. Okay. The other way to do it. Okay. I know it's 280. Okay. I know that this is 280, and I'm adding another 500 milliosmol. Okay, in 5 liters. So each liter will gain 100 milliosmol. So like you can calculate that way as well, and you'll get the same answer. Okay. All right, so let's go back and answer all these questions. Okay, so the solution is hyperosmotic, okay, because there's much concentration of solutes, okay. What is the concentration of non-penetrating solutes? Okay, so the concentration of non-penetrating solutes is, so okay, so this is hyper, okay, this is 250 NaCl. What is the concentration? 300. Okay. Okay, so lower concentration of salt, higher concentration of salt. So salt, okay, will flow into the cell. Okay, so water will enter the cell. If you look at our conditions, it went from 300 and then it went to 280. So water will enter the cell. Okay, so based on my answer in D, the solution is hypo. Okay, so while it's hyperosmotic, it is hypotonic. Okay, so okay. Okay, there, there. Okay. What happens to the body's solution? Okay. It increased, right? So it increased. Okay. So the hyperosmotic, I think we already answered that. Okay. So what happened to the ICF volume? The ICF volume increased. It went from 2 to 2.1. Okay. This means the added solution was, okay. So yeah, you should realize that the same thing. The solution was hypotonic. Okay. Okay, so if you know the starting conditions of the body, you should know the composition of the solution you're adding. You should be able to describe the solution's clarity and tonicity relative to the body's question, blah, blah. Okay, so this type of question, one of these type of questions will show up on your exam, okay? Exam 1, okay? Okay, so you can want concept check questions, I believe it's in your book. Okay. Oops. Clear before I move on to the next slide. Okay. Okay, so here you go. Okay. Okay, so here are some common IVs. Okay, so if they want to get things into you, just solution is put normal saline. Okay, normal saline is isoosmotic, isotonic. Okay, everything is matches. Okay, um, okay. If they want to put sugar into your body, they put 5% dextrose and 0.9% saline. This is like a sugar solution. So from the point of view of the cell, okay, it's isotonic, so your cells don't pick up volume. Okay. Um, okay. So if you're dehydrated, then they want to um, if you're dehydrated, then they want to give you pure water. Okay, water with 5% dextrose. Okay, D5W is isoosmotic because of the 5% dextrose. Okay, the 5% dextrose makes it isoosmotic, but is hypertonic because sugar does not cross the the barrier, the cell membrane, so water comes in. Okay. All right. Okay. Um, okay. So now half saline is hypoosmotic and hypotonic. So again, all the hypotonic solutions, okay, water comes into the cell. Okay, I don't know of any conditions where you would like put in a hyperosmotic solution or hypertonic solution. Okay, unless you drink like way too much fresh water or something like that. Okay. All right, I will stop right here. Okay, for part one. I think there will be 3 parts to this actually. So sharing.